Hi, welcome to Mathematics with Tom. I'm Tom, and today we're going to talk about the inverse matrix, and we're going to learn how to find it. So let's come over to the chalkboard and we'll get started. So today is the inverse matrix. Okay. So I want to do a review of the idea a little bit. And we did this before, but let's just take one more look. Remember what we said? We said if you have a problem like 3x equals 6, that you can multiply this by the inverse of 3 times 3x to get 3 inverse times 6. Well, the number times its inverse gives you the identity, which in the case of numbers is just 1 times x equals the inverse times the number. And our final step is that the identity times the number, or the variable, is very simply the variable. So, and in matrices, it works the same idea. And that is that you start with this problem that some matrix times a vector equals a number. Well, if you multiply this, A inverse times AX equals A inverse times B, exact same set of steps. Well, the inverse, the matrix times its inverse, this gives us the identity of matrices times x equals A inverse B. And finally, the identity times the vector just gives us the vector. Okay, so today we're looking here, these are matrices. And these are just like what you learned for just simple equations. Now, there's one more property here. And that was that if we change the right side ever so slightly, changed it to 0, then we knew what x has to be. X has to be 0. So that's the other thing here that we're going to take a look at. Is what does this tell us about inverses? What does it tell us about inverses? Okay. Well, a few things. If I take, let me write it this way. Say I take the inverse times the matrix. Well, we're going to get the identity matrix. Well, the other question is what if we switch the order? What if I, sorry, didn't do anything there. What if I switch the order? In other words, is A times A inverse also equal I? And the answer is it does. And I want to show you that it's unique, that there's only one matrix that becomes the inverse. So let's do this. If we have some matrix A, and I multiply it by some matrix C, and I get I, so we're talking C in this case is a right inverse, meaning this one, this case, and if I have some matrix B times A, and that equals I. This is a left inverse. Let me write that. B would be a left inverse. C is a right inverse. So the question is, does C equal B? Let's find out. Let's find out. So let's take this. We know that A times C is equal to I. Well, what do we have? This is a little proof. That's what this is a little proof. So when you start a proof, you start with something you know, and then you try to see if you can figure it out using the information you're given. Well, here I've got AC equals I. That was given to us. But look at what I have over here. I also have B times A equals I. So notice that's a left inverse. So what if I write this? B times AC. So if I multiply on the left here, I'd multiply the left here. Now, we've already said that matrix multiplication is associative. So what if I look at this? BA times C. And B times I, well, that's just B. Well, what does this give us? This gives us B times A, but B times A is I. And I times C, that's just C. And sure enough, what this means is that A inverse on the left is the same as A inverse on the right. Okay, there's our first property of the inverse matrix. So let's come over here. We're going to do another one. Suppose that AX equals 0 and X is not the 0 vector. Okay. I'm going to talk about that in a moment. Show A inverse does not exist. Okay. So I want to stop here for just a second because we need to think about this. And what we need to think about was that example we've done prior where we saw that you can have, once you start dealing with the matrix equation, let me come back here. When you have the matrix equation, we actually found an example of a matrix times a non-zero vector that gave us 0. So this is a concern in matrix multiplication that notice down here I didn't write x equals 0 because sometimes it's not true. Okay. All right, so suppose that x is not 0 because if this is 0, obviously this is true. But what if it's true when it's not 0? Well, let's see. So trying to show something does not exist is kind of difficult. So this is a proof by contradiction. Proof by contradiction. So that means that assume that what you're trying to show is not that way. And then show that if being not that way produces garbage, then you've proved it. So let's do that. Let's do that. So let's do this. Suppose what? Suppose A inverse does exist. A inverse does exist. Okay, well, what would we do? Well, let's take a look up here. So I have this problem that A times X equals 0. Suppose A inverse exists. Okay, let's multiply. A inverse A times X equals A inverse times 0. Now, this is just a matrix or a vector full of zeros. Multiply it by a matrix. Clearly, this is going to be 0 on the right-hand side. So, what do I get? So on the right-hand side, I get 0. A inverse times A, that's just I, or just I times X, that's just X. Well, what do we get? We have X is 0. But wait a minute, X is what? Not 0. This is important. What it tells us is that if X is not 0, then that matrix will not have an inverse. And it also tells us the opposite, that if we have an inverse, then we also know this. if a, oops, let me correct that. The contrapositive of that is if A inverse exists, then x equals 0 for ax equals 0. Okay, that's important. We need that. So now we know about our inverses, and I think we're ready. I think we're ready to ask or to find the obvious question. That is, okay, great, we know this about them, but how do I find one? That's the obvious answer. So let's take a look at this. If I have I is in R2, then what was I? That meant that I looked like this, 1, 0, 0, 1. That's the identity matrix in R2. And if the identity matrix is in R3, then I is 1, 0, 0, 0, 1, 0, 0, 0, 1. And it just continues on indefinitely. Whatever space you're in, I, the identity, is always a square matrix, the same number of rows as there are columns. There's always ones only on the diagonal. Every other entry into the matrix is 0. Okay. Let's take a look at our identity matrix. So what we do is we have some special notation for it. And let's all write it this way. And that is we always refer to this first vector, or in this class, we'll refer to it as E1. Our second column vector of the identity we'll refer to as E2. And the third column would be E3. If we were in R4, then we'd have an E4, and that would be 0, 0, 0, 1. Now, this is a contextual way of thinking because this matrix up here is also written as E1. And all that means is that in the first position is the 1. This is the second vector, E2. Again, the 1 is in the second position. But you always have to think about this E1 is not this E1. It depends on what space you're working. So there's an awareness that needs to go with these. Now, let's try this. Let's do this. I'm going to use a, let's do this. Let B equal 1, 2, 3, 6. Find B inverse. Okay. Right off the bat, I'm a little suspicious of this, and I'm going to tell you why. My concern is that, notice that if I take the first column of B and I multiply it by 3, I get the second column. This second column is a scalar multiple of this first one. So that seems strange. Let me think about that. Well, would it even have an inverse matrix? Let's try this. If I take B, x equals 0. Let's write this out. This is 1, 2, 3, 6. Can I come up with some vector x and then 0, 0? Let me write that first. Okay. The question then is, can I come up with some vector x such that it's not 0 that gets me here? take a moment and see if you can come up with, is there a way to get to 0 other than 0? Here's what I'm thinking. I know that the second column is 3 times the first. So what if I just take and multiply the first one by 3 and then subtract the second one? Well, this is 3 minus 3 is 0. This is 6 minus 6. This is 0. Wait a minute. This is x is not 0. What does that mean? That means we look back to what we had shown here. Suppose, I used b, suppose bx equals 0. Okay, I did, right here. And then it says, and x is not 0, all right? What is x? It's 3 minus 1. It's not 0. And what happens then is if x is not 0, we know this. We know that b does not have an inverse. Okay, so b does not have an inverse. Okay. Okay, so you always have to be aware that we tend to default to thinking immediately jumping towards what we're after, but now there may not be anything to get after. So let's try this. Another example is, let's do this. Let A be the matrix 1, 2, 3. Well, we know we can't put a 6 there, so how about 4? Let's try that. So notice that I can't multiply the first column and get to the second column. So because I can't do that, I'm pretty sure that there is an inverse for A. All right, let's do this. Now, I need some vectors for A. Let's say A inverse has a column of x1. Sure, how about just an x vector and a y vector? Who knows what they are? We'll find them. Maybe there's an x and a y. Okay, now, what do we know? Let's think about this. These in this case, these are unknowns. That's what we have to find. So if there's an inverse, well, then that means A times A inverse. That should get us to our identity. Now, I could have taken A inverse A. I didn't by design because I looked in here and said, well, this is a lot like solving for my unknowns of like the matrix equation AX equals B. Watch this. Well, this is A times some unknown X times some unknown Y. And look at this. We even know the columns of I. There's E1 and an E2. So, okay, this gets better. This says that A times X equals E1, and also says that A times the vector Y is E2. Now, think about this. We know how to row reduce and solve this. We know how to row reduce and solve this. Here's the interesting part. The row reductions for solving that are the exact same row reductions for solving this, because the E1 and the E2 will just be a result of the work we do on the matrix A. X and Y will be unchanged. So we can do this. We're going to write this. So we're going to we're going to do this all at once. We're going to do the augmented matrix. Instead, the augmented matrix for A A inverse equals I. Okay, well we know A, that's 1, 2, 3, 4. And remember when we wrote this, we just read a bar. We just put a bar to represent the variables or the components of the unknown because they're unaffected by the row operations. And then, well, what does it have to equal? Well, the first thing it has to give me is E1. E1 is 1, 0. The second problem I have to solve is for E2. 0, 1. Now, that's what we have to solve. So, I think I'm going to start by working on row 2, and I'm going to subtract 2 row 1s. So let's write an arrow. So I have 1, 3, 1, 0. My first row is unchanged. So 2 minus 2 is 0. 4 minus 6 is minus 2. 0 minus 2 is minus 2. 1 minus 0 is 1. Now, you could solve this here. You could. We're going to take, we could use back substitution. So here we could solve by back substitution. Okay. That, solving by back substitution, this is actually what was proposed by Gauss. Get your matrix into the upper triangular form, and then you can very simply say that -2 times something would give me -2, obviously. Obviously, your answer would be 1. And then it would say put that 1 back into here. You'd have 1 times a variable plus 3 would have to give you a 1, and you can solve this. Now, we're going to go a little bit further. A little bit further. You ready? First thing I'm going to do now is this is upper triangular. So now I have essentially made U x equals, I'm going to put a capital C for the matrix of C, not just a single vector. Here's what we can do. Now we work backwards. Work the other side of the diagonal. Work the other side of the diagonal. So you can do this in a few different orders. I'm going to first divide everything by -2. So I'm going to take -1/2 times row 2. -1/2 times row 2. And you don't have to do this. I'm going to put my result. I need more space. I'm going to go to the other side of the blackboard. If you're taking notes, all you have to do is just go down a line. You don't have to go to the other edge of your paper. So let's come over here. Okay, so I'm going to pick up my result. My result is going to be 1, 3, 1, 0, 0, 1, 1, minus 1/2. Okay. So now this is our new pivot. So we had to work down the diagonal. Now we work back up the diagonal, meaning what we want to do is get zeros, we want zeros above the diagonal. So here's what we're going to do. I'm going to work on row 1 by subtracting 3 row 2s. So I'm going to have my first row becomes 1 minus a 0, 3 minus a 3, 1 minus 3 for minus 2, 0 plus 3 halves. Oh, goodness. 3 halves. And my second row remains the same. 0, 1, 1, minus 1 half. Oh, my. Oh, do you see what we just did? Isn't that amazing? You may not see it, and that's okay. On the left-hand side, I have ix. And on the right-hand side, or actually, let me write it this way. I've solved this. I now have ix equals this vector minus 2, 1, and, vector. And what else do I have? Because I solved both of these at the same time. I have iy is equal to 3 halves minus 1 half. Oh my, there it is. But what is x and y? X and y, those are the column vectors of the inverse matrix. In other words, what I have right here is I am at the problem the augmented matrix of A inverse. That's what this equals. Okay, so A inverse, let's write it down, is equal to minus 2, 1, 3 halves, minus 1 half. Now, there is no reason to wonder if that's right. What can you do? You can check. This, remember what the problem that we solved was this, that A inverse times A has to give me I. Well, let's check our work. Let's check our work. That's the beauty of this kind of a problem. So there's no reason to ever get this wrong or to wonder. So let's take this. Let's switch the order. We'll have 2 minus 2, 1. I'm going to write it this way. Let's check. Does A inverse A give me I? Or if you wanted, you could check it as A inverse. Either is fine. That's what we've already shown. So I'm going to try the left side. Minus 2, 1. 3 halves minus 1 half times A, 1, 2, 3, 4. Okay, we're just going to go dot products. Row 1, column 1, that's going to be minus, let's see, row 1 minus 1. That's going to be a minus 2 plus 3 for 1. So now we're going to go row 2, column 1. That's going to be 1 minus 1. That's a 0. Then I'm going to have row 2, column 2. Oh gosh, that's big, huh? Well, that's going to give me a minus 6. Oh, that's 12 halves. That's 0. And then we do that again. I'm going to have a 3. And then minus half of 4 is 2. So 3 minus 2. That's 1, and we got the problem right. Okay, we're going to try one more problem. One more problem. And the reason is I want to show you. Let's try this. We're going to use, I like A, so, or we'll use C. We haven't used C yet. So let's see. Let C be the matrix, hopefully I get this right, 2 minus 1, 0, minus 1, 2, 0, 0, minus 1, 2. Oh, that's not correct. I want to put a minus 1 right there. Okay, now we're going to book. Ready? Let's come over here. So, how do we solve it? What we do is we use the augmented matrix of Ci. And then what we're going to do is row operations, and when we get to I on the left, the result, C inverse. Okay, that's what all of this work that we've done has told us. So let's do that. So Ci, this is 2 minus 1, 0, minus 1, 2 minus 1, 0 minus 1, 2, 1, 0, 0, 0, 1, 0, 0, 0, 1. I'm going to just go through this one step at a time. I'm going to work on, so here's my initial pivot, the 2 in the upper left. I need to remove that. So we're going to work on row 2. We're going to add 1/2. We're going to add half of row 1. I think that should work. Okay. So first row is unchanged. 2 minus 1, 0. 1, 0, 0. Oops. A little more space. So minus 1 plus 1 is 0. 2, this is going to be minus 1/2. That's 3/2. Minus 1. Then I go 0 plus 1/2 is 1/2. 1 plus 0, 0. And my third row is 0 minus 1, 2, 0, 0, 1. Okay. One more step. We have a pivot with zeros. So I come down my diagonal. I need to get a 0 right there. So I'm going to do that. Oh boy. I'm going to work on row 3. And here's the real truth. At some point, you got to just deal with fractions. That's what we're going to do. So what am I going to need? I'm going to need to multiply row 2, I think just by a 2/3. Because 2/3 times 3/2 is 1. Oh, there we go. Okay. So what do I get? First row is unchanged. 2 minus 1, 0, 1, 0, 0. The second row is unchanged. 0. 3/2 minus 1, 1/2, 1, 0. Okay, here we go. So this first one is 0. Minus 1 plus 1 is 0. 2 minus 2/3. Ugh. 2 is like 4, 6. Oh, this is 4/3. 4/3. Okay, and then we're going to do the same thing. So this is going to be.
I'm sorry.
Did I make a mistake?
Yeah, I think you meant you mean 3/2, not 2/3. You flipped it over.
Oh, right here.
Yeah, aren't you using the 2/3 of the 3/2?
Yeah.
Where'd you get thirds? I just don't get where you got thirds.
Oh, this one? Because I have to multiply. I'm working on row 2.
Oh, I'm sorry. I screwed up. Sorry.
That's okay. No, that's good.
I got off.
That's all right. No, this one you have to really, you really have to be kind of in it. And it's easy to mess up, trust, because I've done it,
Yeah.
messed it up.
Sorry, I interrupted that.
No, that's fine. Okay, so we have 2, which is really 6/3, and we're going to subtract 2/3 for 4/3. 0, and then 1/2 times 2/3 is 1/3. So, yeah, 1/3. 0 plus 2/3, that's 2/3. 1 plus 0 is 1. Now, if I was Gauss, I would stop and solve using back substitution. This is called Gauss-Jordan elimination, and Jordan said, well, why don't you just work the problem backwards from here? Work the problem backwards. So in other words, now I need to try to get zeros on the diagonal, or I'm sorry, zeros above the diagonal, and I need to get ones on my diagonal for I. You could work this in either way, but I'm going to decide, I think right now I'm going to just multiply these through to get ones on my diagonal. So I'm going to do that at once. I'm going to take half row 1, take 2/3 of row 2, and 3/4 of row 3. Okay, so we're just going to multiply all those out so I have ones on the diagonal. And what do we get? We have 1 minus 1/2, 0, 1/2, 0, 0. Then I have 0, 1 minus 2/3, minus 2/3. 2/3 times 1/2 is 1/3. 2/3 and a 0. Then I'm going to get a 0, a 0, and then 3/4, 4/3 is 1. 3/4 times 1/3 is 1/4. 3/4 times 2/3 is going to be 2/4, so I'm going to write 1/2 and 3/4. Oh, we are so close. I think we're just down to our last two steps. So let's work on, so now that we're at the bottom, this is my pivot all the way down here. That's my new pivot. So before I leave this pivot, I need a 0 here and a 0 here. This 0 is done, so I just need that one. So what I'm going to do is I'm going to work on row 2, and I'm going to do that by, how about adding 2/3 of row 3. Oh goodness. This is going to be Fractionville. So I'm going to rewrite my first row. Minus 1/2, 0, 1/2, 0, 0, 0, 1. Now, minus 2/3 plus 2/3, that's 0. That's by design. It's the rest of this that gets a bit more complicated. So this is going to be 1/3 plus, oh goodness, 1/3 plus, this is going to be, I'm going to have to come over here and do a little bit of scratch work. Let's do that. Fractions in my head get difficult quickly. Let's do that. So if I have 1/3 plus 2/3 times 1/4, it's going to be 1/3 plus 1/6. This is 2/6, 3/6. That's 1/2. There's 1/2. Okay, and then we do this again. So now I'm going to have a 2/3 plus, so 2/3 plus, that's going to be 2/6, which is 1/3 is 1. And then I'm going to have 0 plus 0 plus, this is going to be 2/3 times 3/4. It's a half. And what else do we have here? Okay, I think we're done with that one. 0, 0, 1. 1/4, 1/2, 3/4. And this is our last row operation because we have, that was the old pivot. We have zeros above, so we move back up the diagonal. Our new pivot, all I need to do is get that negative 1/2 to a 0, and we're done. So I need to work on row 1. I'm going to do that by adding half of row 2. Put my result right here below. So this is going to be a 1. Then minus a half plus a half is going to be a 0, 0. This is going to be 1/2 plus 1/4 for 3/4. Then I'm going to have 0 plus 1/2, 0 plus 1/4, or plus 1/4, yep. And then the rest remains the same, 0, 1, 0, 1/2, 1, 1/2, 0, 0, 1, 1/4, 1/2, 3/4. And there we go. We are now to the augmented matrix of A, C inverse. And that is how you use Gaussian. It's called the Gauss-Jordan elimination to solve a problem, and to, in this case, find the inverse of a matrix. Thanks for watching.